Div1B. The question in brief is we've been given a unweighted tree with n vertices and n minus 1 edges. We need to assign weights to the edges in such a way that the XOR of all the edge weights in every path between two leaves should be 0. And we need to find two values, f1 and f min and f max. So let's define f first. Let's see what is f. F is the number of distinct weights in the assignment. So, for example, in this case, f is 2. In this case, f is 3 because 3, 4, 5. Here because 4 and 5. So, yeah, we need to find the minimum and maximum possible values of f for the given tree. The way we do this is, first of all, whenever we have a tree with queries including XOR, we should keep this in mind that it might be useful to root the tree. The reason for this is uh, if we want XOR to be 0, and also we'll root the tree at a leaf in this case, in this question. So once we have rooted the tree at a leaf, if the XOR between this leaf and this leaf is 0, this automatically, and the XOR between this leaf and this leaf is 0, we can automatically conclude that the XOR between this leaf and this leaf would be 0. The reason for this is, since the XOR between this leaf and this leaf is 0, the XOR of nodes in this okay, this is not a great example. Let's take this leaf, and this leaf. The XOR between this leaf and this leaf, if this is 0 and this is 0, then we can conclude that the XOR between these two leaves are 0. The reason being, XOR from this to this would be equal to the XOR from this to this, right? And we know that the XOR from this to this, XOR this to this is 0. Hence, we can conclude that the XOR from this to the XOR from this to this XOR. Okay, let's call this 1, 2, 3. No. Let's call this A, this B, this C, and this is root. So we know that if XOR between root to B is 0 and the XOR between root and A is 0, this implies that the XOR between root C, XOR C, B is 0. This implies that the XOR between RC is equal to XOR between CB. So we, and since and XOR between AB can be written as XOR between AC, XOR CB. XOR CB we know is equal to XOR RC. This is XOR AC, XOR RC. And XOR AC, XOR RC is nothing but XOR RA. So we've shown that XOR, if XOR of R to B is 0 and XOR of R to A is 0, XOR of A to B would be 0. And this holds for every pair of leaves. So from this observation, we conclude that if we check the cases from the root taken, that would extend to all the leaves. So we don't need to check between every pair of leaves. So with this out of the way, let's see how we calculate f max. Hint is to use powers of 2, because first of all, 10 power 10 power 10, this is a huge number. These weights in this range are allowed. So that's a hint to use powers of 2 maybe. Also, an observation is, if we use powers of 2, uh, then the XOR of powers of 2 cannot be in the set of powers of 2, right? Yeah, so the way we find XOR f max is, we greedily choose powers of 2 as much as we can. So for example, when we are at root, we choose 1. In this edge we choose 2, in this edge we choose 4, in this edge we choose 8. This edge we would have wanted to choose 16, but we can't because we need to make this XOR of the path 0. So we need to choose 1 XOR, 2 XOR, 4 XOR, 8. Similarly, for this edge also we need to choose ones or twos or fours or eight. For this edge we need to choose ones or twos or four, and this way we have to choose the powers of two. Okay. Now a subcase is so yeah. An observation is always the edge weights would be unique. So 1, 2, 4, 8, all of these are unique. The only time ones or two, this is also unique. Ones or twos or four is also unique. The only time the edges are not unique, like this ones or twos or fours or eight and 1, 1. The only time these are not unique is when we have a node which leads to two or more leaves. So, for example, this node and this node, this node leads to two leaves. This node leads to two leaves. So, whenever this is the case, we'll have to decrease um the number of distinct edge weights by the number of leaves minus one. The number of leaves the current node leads to minus one. So the answer finally would be total number of edges minus summation of over all the leaves with leaf number of leaf neighbors greater than one actually, and number of leaf neighbors minus one. This is about f max. Moving on to f min, we make an observation first of all that if all the distances between two leaves are are even, then we can simply assign a edge weight 1 to all the edges, and we'll have the required XOR between every two leaves, that will be 0. So for that case, the answer f min would be 1. If that is not the case, that is, there exists a pair of leaves which have a distance of 1. Okay, so one more thing we need to clarify is that if we establish that from the root all the leaves have a distance even have an even distance, that automatically implies that every pair of leaf in this tree has a even distance between themselves. So the reason for this is, let's say from root to, let's call this a, let's call this b. Okay, 1 2 3 1 2, let's call this this is not a, let's call this a. So we know that A and B both have a distance of have an even distance from root. Now A and B would also have an even distance between themselves. The reason being that uh, the reason being that this edge. Okay, let's the distance between RA. Let's call this C. Distance between RA is equal to RC plus CA. Distance between RB is RC plus CB. Now the distance between AB is CA plus CB. CA plus CB is distance of RA. We know that RA minus distance of RA minus distance of RB is even. That means that CA minus CB, uh, CA, oh, distance of RA plus distance of RB is even. This means that CA plus CB has to be even. So from this observation, we will only checking for the root would be sufficient. So we've established for if for the case when all the distances are even, when that is not the case, when there is a single, even a single pair of leaves which have a distance not even, then the answer would simply be 3. The reason being, we can always populate the edges with 1 2 3 to get the desired result. Let's look at the code very quickly. We store the number of leaves. We store the leaves in a set because we'll have to check whether a given node is a leaf or not. This is checking for f min uh, from a DFS. in the DFS we are calculating the depth of each node and the number of leaf children of each node. Once that is done, for fmin we had two cases, right? This is handling the two cases. For fmax, initialize it with the number of edges, and for every child that is with NLC I greater than 1 or greater than 0, this it's the same thing. Fmax will decrease this amount from fmax.